Ethernet is a tried and tested technology which has been around for over 40 years, and we saw it first standardised back in 1983 as IEEE 802.3. Since then, it's been growing constantly, so it makes perfect sense that we had to use it for video distribution. We saw control move over to Ethernet in the early 2000s, and audio shifted across about 5 years ago. But video is more complex, and therefore it's taken longer to transition. But with 10 gig quickly replacing 1 gig as the norm, we're now able to really replace the matrix switch with Ethernet technology. The software-defined Video over Ethernet Alliance offers the ease of use and performance of the matrix switch, while maintaining the scalability and flexibility of Ethernet. And this is hugely important when meeting today's business needs in Pro AV. So let's take a look at how this is all achieved, because SDVOE changes the way that system design is handled. In the old, traditional world, a system is a very carefully configured mix of hardware. The matrix switch at the centre, surrounded by transmitters and receivers, specialised processors like multiview, video wall scalers and so on. We might also have extra peripherals like USB or even an entire subsystem. And these systems do work, but they're time-consuming and costly to design. And their complexity also makes them difficult to install and troubleshoot. And all of this extra time is costing the designer and the installer time and money. With SDVOE, every system is virtually the same design. Each source is attached to an encoder, each display attaches to a decoder, a 10 gig switch sits in the middle and connects all the devices. And now, software takes over the system to tell it what it is: a matrix switch, a KVM switch, a multi-view processor or a video wall scaler, or a combination of any of these things. Whichever application you need today, it can be changed tomorrow with a simple reconfiguration of the software. And this is what software-defined video is all about. The system designer saves time, the system installer saves headache, and the end user enjoys a flexible system that can easily adapt to changing missions. Thanks to 10 gig networks, matrix switch performance is matched with SDVOE technology. The decoder is fully synchronized with the signals going into the encoder, with a maximum latency of just 0.1 milliseconds. Now, in layman's terms, that means that what comes out is exactly the same as what goes in, just like a matrix switch. And this process also works with multiple decoders, and the signal is outputted exactly as it is, regardless of the format. And this latency-free quality matching performance is vital for those cases where latency-free is paramount. If you require an operation and the surgeon is relying on a 4K monitor to see exactly what he's doing, the last thing you need is latency, right? I'm sure I made that incision. Ooh, oops. Whenever video is compressed, artifacts will appear on the screen, and the bigger the screen, the more noticeable those artifacts become. Now, with 1 gig networks, there's little choice other than to massively compress the original image. And in today's 4K world of video, it's not really acceptable to consume most of a 1 gig network with AV. No matter how clever the compression codecs are, it still has a huge effect on the data performance of that network. And while features like quality of service can help, it only lets you choose which compromises you want to make. Using 2 networks together isn't really a great solution either. Why would you have a 1 gig network for data and a separate 1 gig network for video? You may as well leave the matrix switch in place and let it drive the video distribution properly, rather than manage 2 separate networks. The solution already exists with 10 gig networks. AV and IT users can coexist on a single network with absolutely no compromise. Integrators only have 1 network to manage, and the video quality is completely unaltered without any latency. So, how does it work? Well, in order to turn a video signal into packets of data which can then be sent across a network, codecs are used. Let's take a look at how codecs actually work. Codec is a shortened form of two words, coder and decoder. So, in the world of video distribution, a codec is a piece of algorithm which turns raw video from a source into a bit stream, then brings it back out again at the display. There are many codecs, each designed to achieve a particular purpose, and each codec has its own set of trade-offs compared to the others. An easy way to understand these trade-offs is by considering the codec triangle, which illustrates the trade-offs between the three most important characteristics of a codec: bandwidth, latency, and image quality. Achieving lower bandwidth without significantly impacting quality requires more sophisticated algorithms. These take longer to run, so latency goes up. Keeping latency low and quality high means compressing less, so bandwidth goes up. Streaming a low latency video stream with low bandwidth has a drastic effect on the quality. Bandwidth is the amount of data consumed by the encoded stream and is measured in megabits per second or gigabits per second. Quality is how similar the pre-codec and post-codec images look. Latency is how much time passes between an image being fed into the encoder and the same image being displayed on a display after being decoded. Let's use a real-life example to compare these codecs. In each example, we want to distribute a 4K 444 60Hz stream, which we can see has a bandwidth of around 12 gigabits per second. Let's start with the MJPEG 2000 codec. This is an intra-frame codec, so it compresses one frame at a time, giving it a typical bandwidth requirement of 600 to over 900 megabits per second. So it's fair to assume this codec was designed specifically to fit within a 1 gigabit per second environment. But how does that affect the latency and the quality? If we use the codec triangle, we can see this 12:1 compression means there is very little bandwidth left to adjust our latency or quality performance. So, what we see is what we get. Quality is okay, latency performance ranges from not bad to unacceptable, and bandwidth pretty much uses up 1 gigabits per second. Nothing really wins in terms of performance. It's just, well, okay. Let's shift codecs, and this time we'll use the H.264 codec to send our 4K 444 video stream. H.264 is part of the interframe family, so rather than compress each frame, it cleverly compresses a number of frames at a time, giving it an average bandwidth requirement of around 30 megabits per second, making it the perfect codec to use for wireless and mobile applications. So how does this affect the latency and quality? Back to the good old codec triangle. Pushing a 12 gigabit stream into 30 megabits per second means that H.264 has a massive compression ratio of around 500 to 1, and to achieve this requires incredibly complex algorithms, which unfortunately have a dramatic effect on the latency. However, because the bandwidth value is so low, there is plenty of headroom to trade some of the latency while maintaining quality. Here, latency and bandwidth can be adjusted within the triangle to suit the environment while maintaining a reasonably high quality image. If you're watching a Netflix movie, for example, on your mobile, it doesn't really matter how long the algorithm takes to compress the image, as long as it looks great. Okay, let's shift codecs once more. And this time, let's use the SDVOE codec to once again send our 4K 444 video stream. The SDVOE codec is part of the pixel pipeline family, which means that only a few lines of each frame are compressed, resulting in a much lower compression ratio of around 1.4 to 1. This means A 12 gigabit stream will easily fit within 9 gigabits per second. But how does this affect the latency and the quality? Once again, let's apply this to the codec triangle. The bandwidth requirement is 9 gigabits per second, and thankfully, the growth of Ethernet supports this. As with 1 gigabit per second switches did 5 years ago, 10 gigabit per second switches are quickly becoming the normal accepted standard of switch. So, bandwidth isn't an issue. The 1.4 to 1 ratio means that our latency values are so low they are non-perceptible to the human eye. So, latency isn't an issue either. And thanks to an extremely low compression ratio, with the SDVOE codec, we're left with a perfect image quality which is mathematically lossless for most content. Finally, network designs have a clearly thought out topology for a project. So regardless of which engineer has to support it, he has all the information he needs to identify exactly how the network may have changed from when it was originally configured. Every project should have its own network design, which includes a topology layout of each connected host, and details of how each host is connected to each switch within the network, including any cable markings, setup details for routers or switches, and tables identifying key information about each host within the network, such as login information, network addresses, locations of the equipment, and so on. This information is essential when troubleshooting because when networks go wrong, it's usually caused by people and not faulty equipment. Now it's your turn, so here's a little quiz. See how you get on with these questions, and don't worry if you're not sure of the answers, we'll show you where to find them in the video. Good luck, and we'll see you soon.